Alright, silly people, here's the situation. This is actually a problem that I did before, but a clever commenter on that video said that I did it wrong. And they're right, I did do it wrong. So I'm just going to do the whole thing again, just from the top. Because the issue that I had with it was pretty fundamental to what the problem actually is. So here's a cylinder. It has a height h and a radius r. And we are meant to find the condition in which the equation that involves these momenta of inertia here, I think it's called the characteristic equation or something like that, is the same as that for a sphere. Now, the sphere in this formalism for the principal momenta of inertia, all of the momenta of inertia are the same for the sphere. So we have to find the condition where that is true. Where the cylinder only has Ixx equals Iyy due to symmetry already. So we just need to find Izz and set it equal to what Ixx is once we solve for both of them. The Izz integral is going to be the one that's actually more easy to do. So let me actually go through the equation for this. To find your principal momenta of inertia for coordinates p and q, you would do the volume integral of the mass density times this r squared times the delta function of those two coordinates p and q minus xp(xq). And so for Ixx, that is actually going to look like the integral over the volume of the mass density times r squared minus z squared. What I didn't realize is that that r squared in there is actually the spherical r squared, not the cylindrical r squared. But there is a transformation between them because, and I'm writing Izz first, not Ixx. I better specify. I'm also going to treat the mass density as constant because it's going to end up not mattering either way what it is. But then it's an integral from h over 2 to h over 2 z. It's an integral from 0 to 2 pi of theta. And it's an integral from 0 to r for rho. And then r squared is going to go like rho squared plus z squared in cylindrical coordinates. And then it has a minus z squared on it from before. And the Jacobian is rho d rho d theta dz. This z squared actually cancels out this z squared, so it's just an integral over rho, which is relatively easy to do. So since there's no terms which involve z in there, the z integral is going to give you an h. No thetas, so the theta integral is going to give you 2 pi. The r integral, or the rho integral, I guess, is going to give you r to the fourth over 4, because it's rho cubed in there. Yeah, so simplifying this a little bit, you're going to get rho h r fourth pi over 2. Glorious. So then where does Ixx come from? It's a little bit more of an involved integral because it's the integral of the mass density times r squared again, but I'm going to go ahead and decompose it into r squared plus z squared, and it's rho squared plus z squared minus x squared dv. So let's also set the integral up and move the mass density outside, so it's h over 2 to h over 2, 0 to pi, and it's going to be 0 to r of, and then x squared goes like rho squared cosine squared theta. So actually, we've got a rho squared term here times 1 minus cosine squared theta for the rho squared and the x squared term, and also a z squared term. And the Jacobian is still rho d theta dz. So going through the integral now, we've got h over 2 to h over 2, 0 to 2 pi. It's rho cubed for the term involving the 1 minus cosine squared guy, so it's going to go like r to the 4th over 4 for that bit, and 1 minus cosine squared theta is sine squared theta. You guys probably know that. And then the z squared term had a rho attached to it, so it's going to go like z squared rho squared over 2. But go ahead and evaluate it at r, so it's z squared r squared over 2. This has to be integrated from 0 to pi for theta. So it's a pretty common integral that sine squared d theta from 0 to 2 pi is just pi. So I'm not even going to prove it here. It's just pretty common. So it's r fourth pi over 4 plus, and then z squared r squared times 2 pi, right? Because there's no theta attached to it. You're just going to evaluate it straight to 2 pi. That you have to integrate over z. So let's factor through the r squared pi stuff at least now. Rho r squared pi over 2, and it's going to be the integral from minus h over 2 to h over 2 of r squared over 2 plus z squared, and then yeah, just z squared actually. And that's not even true. There's not going to be an over 2 out here. But there is going to be an over 4 in here, and then the z squared term is hanging out by itself. That we integrate over z. So we're going to get rho r squared pi. Just integrating over z now, it's going to be r squared z over 4 plus z squared, or z cubed actually, over 3. Right? That we integrate from minus h over 2 to h over 2. Sure. So just evaluating at the endpoints now, we've got r squared over 4 times h over 2 plus h over 2, so r squared h over 4 plus, and then it's h over 2 cubed goes like h cubed over 8, and 3 times 8 is 24, and then they add up, so you get h squared, you get h cubed over 12. Yeah, h cubed over 12. Cool. So let's also now yeah, let's pull out the factor of h squared, or just h, and 1 over 4 now, to get rho r squared pi h over 4 times, r squared plus h squared over 4. No, 3. You see what I mean when I said this problem was a little bit more involved? But now that we have this, we can go up here and we can set it equal to this now. So looks like we've got rho h r fourth pi over 2 equals rho r squared pi h over 4, and this is multiplied by r squared plus h cubed over 3 stuff. Let me yank this over here. R squared plus h squared over 3. Okay, cancel out the pi's on either side, cancel out the rows on either side. By the way, that's why the mass density function doesn't matter. Cancel out the h's here on either side and decrease the powers of r, so now we have just r squared equals 1/2 of r squared plus h squared over 3. Just factor that 1/2 through, so you get r squared over 2 plus h squared over 6, and then subtract both sides by r squared over 2, so you get r squared over 2 equals h squared over 6. And then multiply both sides by 2, so you get r squared equals h squared over 3, and then d, the diameter of the cylinder, is equal to r times 2. So let's use r equals d over 2 now. So we've got d over 2 squared equals h squared over 3. Actually do the square now, so d squared over 4 equals h squared over 3. And then solve it for h over d. Solve it for h over d. So you get h squared over d squared is equal to 3 over 4. And then you take the square root of both sides, and you get that the height to diameter ratio is equal to root 3 over 2. And that's what you should have gotten all along. My bad.